Hello everyone, I'm Michael 4238. I believe everyone who has been studying in universities has learned something called Cauchy Inequality. And most of people, I guess, thought it was boring and useless, or you may never use it in anywhere else except mathematics exam. However, it is considered to be one of the most important inequations in all of the mathematics. It could be used in proving other inequations and calculation of limits and mathematics analysis of infinity progression. What's more, some questions in Chinese college entrance examination could be easily solved by using Cauchy Inequality. And this is also one of my favorites. So today, I want to share some of my understanding about Cauchy Inequality with you. But before we get into that, I want to introduce you the Augustin Louis Cauchy, a profound mathematician who was reputed as a pioneer of mathematics analysis. And he was the first one to state and prove the theories of calculus rigorously and lay the foundation of calculus. For example, the concept of limit, which appears everywhere in calculus, is first clarified by him. Born in a French senior official family, Cauchy had made an acquaintance of many great mathematicians at that time in his young age, such as Laplace and Lagrange. And that suggests him will be a successful mathematician in his future. In his student age, because he didn't talk much, and even if he talked, it was very brief and confusing, so he got a nickname called Beetleborg. Well, to me, nowadays I think this word should be used to describe the student who is learning Cauchy's theory rather than Cauchy himself. Now, let's get to the equation itself. And I hope it won't remind you how the Beetleborg are tested. The inequation states for any real number, ai and bi, and I represents the positive integers from 1 to n, there is always an equation like the square of the sum of all the ai times bi is always no greater than the sum of all the ai squared times the sum of all the bi squared. And this inequation could be also written as this form. And when and only when there is a fixed ratio between every pair of ai and bi, the left-hand side of the equation is equal to the right-hand side. At first glance, you may think it is complicated with n figures times n figures at both sides. But if you look at the structure carefully, you can find a beautiful similarity between the left-hand side and the right-hand side. Let me show you. First, we can all find parentheses at both sides. Well, frankly, who cannot? And inside the parentheses, they are the sum of m products. For example, at the left-hand side, it is a1 plus b1 until am times bn. And at the right-hand side, it is a1 squared until an squared and b1 squared until bn squared. And both sides consist of a product, which is the parentheses times together. For example, at the left-hand side, it is a square of one parenthesis, which is a parenthesis times itself. And at the right-hand side, it is two different parentheses times together. Now, the amazing thing is that you could prove it by algebra, or by geometry, or by trigonometry, or by even calculus. And no matter which approach you use, you will finally come to a successful conclusion. What I'm going to do next is to prove this equation in one simple way, and you will find it is wonderfully provable. And I'd like to prove it by using vectors. First, as we all know, vector A dot vector B is equal to the magnitude of A times the magnitude of B, then times cosine theta. As the absolute value of cosine theta is always smaller or equal to 1, then we can have the vector A dot vector B is always greater or equal to the magnitude of A times the magnitude of B. And with this conclusion, we can prove the Cauchy equality. Now, we assume that in n dimension, there are two vectors, A and B, in which A1 to AN and B1 to BN are two sets of random real numbers. Also, according to the basic knowledge about vectors, we can have the magnitude of A and the magnitude of B and vector A dot vector B calculated by this. And with the previous conclusion we already have here, we can have an equation like this way. And square both sides, we can have this, which is exactly the same as the Cauchy equation. And now comes to a special situation, which is when the absolute value of cosine theta is equal to 1. When this happens, the theta, which is an angle between vector A and vector B, is 0 or 180 degrees. And when this happens, there is a fixed ratio between every corresponding coordinate of vector A and vector B. And this could be written as this. This lambda, which is a fixed ratio, is a fixed real number. And then everything is matched with the original Cauchy equality. So we can say that the original Cauchy equality is proved. Now we have already proved the equation. Now comes to how to use it. As I mentioned before, some questions in Chinese college entrance examination could be easily solved by using Cauchy equality. And here is a question from the past paper in 2008. The question states, for a platform with coordinate system x or y, point xy is a moving point moving on an ellipsis, with an equation like this. And he asked us for a maximum value of s, which is the x plus y. Usually, the questions related with ellipses are complicated because there are squares in the equation of ellipses, so as this one. And this one is even more confusing because he asked us for a maximum value, which is related with a moving point. But if we use Cauchy equality, this question could be easily solved. First, we take these four values as A1, B1, A2, and B2. And in order to create an equation like Cauchy equation, we can have this equation. And take these four values into the equation, we have the square of x plus y is always smaller or equal to 4. Then we can say that x plus y is always smaller or equal to 2. In order to reach the maximum value of x plus y, then we have to make the left-hand side of the equation equal to the right-hand side. And then we have a fixed ratio situation, which is like this. And then we can get a relationship between x and y from the fixed ratio situation. Then take this relationship into the ellipses. We can have the exact value of x, the exact value of y. Then we have the maximum value of s, which is equal to 2. Then the question is solved. Now we know that Cauchy equality could help us solving some confusing questions. It could simplify difficult questions into one or a set of equations. But to me, the interesting thing is not solving difficult questions in the simple way it provides, but the procedure I can prove it in many other approaches. For example, apart from the vector way I have introduced, I can still prove it in algebra or geometry or by trigonometry or even calculus. And no matter which approach I use, as I said before, I can come to a successful conclusion at the end. And that is exactly what fascinated me most, by exploring the pattern between numbers to find the beauty of pure mathematics. Before Cauchy's death, one of his friends told him to slow down his pace of work so that he may pass the illness. But Cauchy said this in response: "Dear sir, men pass away, but their works remain. Pray for the works." I understand this sentence as, the real important thing about mathematics is not how many questions I've solved or how many marks I've got in the exam. It is about the joy and the sense of achievement I've got by exploring the relationship between numbers and seeing how they are changed. And that joy I've got is ever growing. Well, that's all about my talk. about Cauchy equality. Thank you.